Howdy, y'all. Today we're doing a lesson on the NAND gate. So in this lesson, we're going to learn about our first universal gate, which is called the NAND gate. And that means, NAND means not and. It's basically the opposite of an AND gate. So we're going to look at the basic function, see how it's the opposite of a NAND gate, of an AND gate. We are going to see how you can use NAND gates to replace all three gates in AOI. We will use the ability to do that. So we have circuits where we use AND or an inverter gates. We've been using those. Now we're going to see how we can translate those circuits into using only NAND gates. And the reason that we would do that is because if we can make a whole circuit out of a single type of gate, then in a lot of cases we use many fewer integrated chips, which means that implementing our logic costs less. So we'll see by the end of this lesson how we can do that, how by changing from AOI to NAND logic, we can simplify the circuit to the point where it might have the same number of gates or maybe even more gates, but it will actually use fewer ICs. So here's a NAND gate. And if you look at it, the structure of it is it's basically an AND gate with an inverter bubble on it. And that's really what it does. It takes the two inputs. First, it ANDs them together, and then it puts an inverter on top. So you can see if you have X and Y as your inputs, your output would be X and Y with an inverter over both of them, right? It ANDs first and then puts the inverter. Then if you remember, theorem 20 was our De Morgan's theorem that said if you have an inverter over X and Y, you can break it apart into not X or not Y. And if you think about the logic or the truth table, if you remember for an AND gate, or I'll write the AND here. So this is NAND. And I want to just, for memory's sake. Yeah.
Is there like a specific thing that we're supposed to be writing, or do we just like write all of it?
So like you would need to write what the NAND gate looks like. And I would say you would need to copy down the what's it called, diagram here.
Okay.
And you probably don't need the truth table there, but if you have time to write the truth table, go ahead. I want to remind everyone though of the truth table for AND. Right? So I'll just kind of extend the rows out here a little bit. So if we had an AND gate, then our output would be, remember, an AND only throws a 1 when you have a 1 at both inputs. So it'd be a 1 here, and then on every other row, we don't have X and Y. So it would be a 0 on every other row. And then you can see that the truth table for the NAND gate is the exact opposite of the truth table for the AND gate. So that's why it's just not AND. It's like AND, but and if you look at the structure of it, it's AND with a negation. It's AND with an inverter, so it's not AND. So the truth table is the opposite, right? And what it means is um, you're only going to throw a one. This gate will only throw a one if you don't have X and Y at the same time. And so that is the top three rows. The top three rows are where you don't have X and Y at the same time. The bottom row is the only one where you do. So not X and Y, you would get a one anytime you don't have both of them, and a zero if you do have both of them. So that's the NAND gate. Now here's how we use the NAND gate as an inverter. What you do is you just take a NAND gate, and then instead of putting two different variables at the two inputs, you put the same variable. And what happens is the AND part will do this. The AND part will AND X and X, and then one of our Boolean theorems was X and X is just X. So that simplifies to just X when you put an X at both inputs. And then the bubble is the inverter part, so that just puts the inverter over it. So if you take a NAND gate and you put the same input into both inputs, that turns it into an inverter. So that means that when you see a NAND gate with a dual input like this, with the same input, that's the same as if you saw an inverter. So this, I'll draw it down here. So this symbol right here, which says you have two of the same inputs going through a NAND gate, that is logical equivalent. Triple equal sign means logical equivalent. That's the logical equivalent to an inverter. So a regular inverter just has one input and then it just changes it to not that. This now, if you think about this as being one input, it just splits it into both inputs, and now you have an inverter. So when we're later on, when we're switching out our AOI logic designs for NAND designs, an inverter, you'll switch it out for this. So now we're going to see how to use NAND gates to make an AND gate. And basically, since a NAND is just an AND with an inverter, we can just put another inverter and then it'll turn it back to AND. So, so we're going to use our NAND version of an inverter. So to do an AND gate, if we want to do X and Y, you just run those inputs into a NAND gate, and then the output of that NAND gate just goes into both inputs of another NAND gate. And so what happens is when X and Y go through here, the AND part puts them together as X and Y. The bubble puts the inverter over the top of them. Then running this through the inverter puts another inverter line on top. So we have two inverter lines on top. And then theorem 9 tells us when you have double inverter that they cancel each other out. So that's how we got X and Y as the result. So what that means is anytime we have an AND gate in our design, That's the logical equivalent of a NAND gate going into a NAND inverter. So it looks more complex right now. It looks like, why would I replace one gate with two gates, right? But we'll see how it actually can make things simpler. So this is the NAND version of an AND gate. So next we need to look at the NAND version of an OR gate. So here's the NAND version of an OR gate. And basically it starts off with an inverter for each variable, NAND version of an inverter. So then out here we have not X and not Y going into the NAND. So the AND part will AND them together, but remember they both still have their separate inverter on top of them. So that's why we have this right here. They have separate inverters. They're ANDed together, and then this bubble puts another inverter over both of them. Then we use right here, we used De Morgan's theorem, our theorem 20, to break the top inverter apart. That switches it to OR. And then theorem 9 gets rid of these double negations. So then it's just X or Y as your final product. So anytime you see an OR gate, you can replace it with this 3-gate little conglomeration. So an OR gate, instead of seeing one of these, instead of drawing one of these, instead of that, we are going to draw so 2 inverters there, and then those outputs become the inputs to the last NAND gate. So, and again, you might be like, well, why would I want to replace a single OR gate with 3 NAND gates? But it'll make sense, I promise. So, in a review, this would be a good thing to have in your notes, is this AND gate becomes this in NANDs, an OR gate becomes this in NANDs, and an inverter becomes this in NANDs. Okay, so then we're going to work through together an example or two, maybe, of working through the process of converting from AOI to NAND logic and simplifying it. So first, we're going to talk about the process that we're going to go through. So first step is to take our logic expression and draw the AOI circuit design. Then step 2 is we're going to take the AOI implementation and we're going to take every AND or an inverter gate and replace it with the NAND equivalent. So we're going to do it all in NAND gates. So we redraw that circuit with only NAND gates, and we're only using 2 input NAND gates. We redraw that, and then the thing that we're looking for to simplify is double inversions. If we get an inverter back to back. So remember, an inverter in NAND looks like this. Two of the same input going into a NAND. So if you ever see two of these in a row, you can just cancel them out. They cancel each other out. Because what happens, imagine if you had your signal was X going in. So you got X going in. Well, this is an inverter, so it's going to spit out not X. Then not X is going to go in here. Well, this is an inverter, so it's going to spit out not what I was trying to write. It's just going to spit out X. So logically speaking, if you see two inverters in a row in line, they cancel each other out, right? X at the start, X at the end. We didn't really need these two things, did we? We can just take them out. And then redraw the final circuit. So let's look at an example here. So you can see that, let's verify that we get this logic expression first. So we starting here from C, we have C going into this inverter. So out of that inverter, we have not C. And then this AND gate here is getting B as well as not C. So we have out of the AND gate here would be B and not C. Let's look at this AND gate down here. We've got C coming in and we've got A coming in. So the output of that AND gate will be A and C. And then you can see this OR gate here is just going to put an OR between the B and not C and the A and C. So you can see that that is the correct logic expression for this circuit. So the next thing, now what we need to do is we need to identify each one of these gates and replace it with the NAND equivalent. So the OR gate, the NAND equivalent is you split and you have that input go to both inputs of the NAND gate. So twin inputs on a NAND gate is an inverter. So we just put it like that to replace the inverter gates. The AND gate is a NAND with an inverter after it. So every AND gate will replace with a NAND and then an inverter after it. And then the OR gate is the one that has two inverters that input into a NAND gate. So for step two, we're gonna, or I guess step three is when we redraw with these gates instead. So remember the inverter was here. So we split it so that both inputs get the same variable, and then that turns this into an inverter. Then we've got our NAND with an inverter after it for both of our AND gates. So this was our AND gate was here. And then our OR is here. And this was our inverter. And then when you look at, once you redraw it with all your NAND gates, then we're looking for any time we have two inverters in a row. So here's this, let's see, let me get my flashlight, laser pointer. So this one, here we have an inverter, but the next thing is a NAND gate, not an inverter, right? But here we have an inverter, and the very next thing is, look at splits off, that's another inverter. So here we have back-to-back inverters. So this pair of inverters cancel each other out. And then down here we have another pair of back-to-back inverters. So these inverters are going to cancel each other out. So now our circuit gets simpler, right? We'll still have this inverter, then we'll go through this NAND gate, and then the output of this NAND gate will go directly to the input of this NAND gate. And the output of the NAND gate down here on the bottom will just go directly to the input of this NAND gate here, and we've simplified our circuit a little bit. So when we then redraw after we cancel out any back-to-back inverters, our circuit is going to look like this. So it has 4 NAND gates. And we can verify that it has the same logic value. So let's do that. So right here we have C going through an inverter. So then out here we have not C. And then going into this NAND gate, we've got B. So coming out of this NAND gate, we have, so the AND part puts them together. So B and not C. And then the bubble puts, I need to write that better. That's the not C got connected to the B. So we got the AND part of the NAND, ANDs them together. It won't let me draw slow. So the AND part ANDs them together, and then the bubble part puts the inverter over both of them. So then let's look at this NAND gate down here. We got C going in and A going in. So the AND part puts them together, A and C. The bubble part puts the inverter over both of them. So now, coming out of this NAND gate, what the AND part is going to put the not AC and not B and not C. It's the AND part will AND them together, and then the bubble part will put an inverter over both of them. Now, what I'm going to do is I'm going to simplify this a little bit, right? I have this top inverter. I can use theorem 20 to break that apart. So I'm going to use theorem 20 to break this top inverter apart. And what that'll do is it'll break it apart and it'll put an OR in between them. And then what do I have on this side? I have not A and C. And on this side, I have not B and not C. And then if you remember, theorem 9 was the one that says not cancel each other out. So then we just get A and C or B and not C. And that was the same expression that we got before when we had AOI, logic implementation. So let's look at the comparison then. Why would we want to do this? Why would we want to change from AOI logic into NAND only logic? Well, if we look at it, the little charts down here give you this information. This is the inverter. This is the AND gate. This is the OR gate. So we need one inverter. We need 2 AND gates, and we need 1 OR gate. Well, here's how the integrated chips come. They come as hex inverters, so there's 6 inverter gates on one chip. So even though we only need 1 inverter, we would have to bring a whole chip in that has 6 inverters. So we're wasting 5 inverters. We're not using 5 5 of the inverters on this chip. For the AND gate, we need 2 of them. Well, they come in chips that have 4 gates each, so we would need 1 of those chips, but we're only using 2 of the AND gates in it. Then for the OR gate, we only need 1 OR gate, but the OR gates come with 4 gates in a chip, so we would need a chip for that. So on our breadboard, we would have 3 separate integrated chips, and so a total of 3 integrated chips, right? 3 different integrated chips. But by switching it over to NAND technology or to NAND logic, we now have, it's still 4 gates, but they're all the same kind of gate. And those chips, the NAND chips are quad, like the AND and the OR. They come with 4 gates apiece, meaning we only need 1 chip to make the same exact circuit work. So that's the benefit of converting from AOI into NAND, is that if we're able to simplify it, we can get away with a lot fewer integrated chips in our design, and fewer chips is lower cost of production. All right, so that is the end of that lesson.